Hello everyone, I am Madhvi Gaur, Assistant Professor, ABES Engineering College. Today I am going to discuss about binary search tree deletion case. This operation can be performed on binary search tree as well as insertion and searching. We can also perform on binary search tree, but I have discussed these two operations in my previous lecture. Today I will focus on the deletion case only. Next, I am going to discuss about threaded binary tree, Huffman coding using binary tree. Let us start with the deletion operation. If I want to delete a node into a binary search tree, then before performing or before directly deleting that node, we have to consider these three cases. Case 1, if a node to be deleted has a no child, it means that node which I want to delete, that node do not have further children. It has no child. Okay. In the case 2, if a node to be deleted has only one child, it can be either left or right. For the case 3, if the node which I want to delete has both the children, then what we have to do? Let us consider all these three cases. With the help of example, we will discuss all these three cases. Okay. For the case 1, it is directly showing, let us assume some binary search tree. Okay, let us consider this binary search tree. And if I want to delete this 29, this will lie into the case 1 because I want to delete 29 and it has no further children. Okay, for the case 2, if I want to, the case 2 is if a node to be deleted has only one child. It means if I want to delete 30 and this 30 only has a one child which is left child, then this will lies for the case 2. And for the case 3, if I want to delete, let us assume some node is there, 27. If I want to delete 28, then this will lie into the case 3, in which a node which has both the children. Then in this case, we have to consider the third case. Okay. Let us consider this example. This is a binary search tree which I have taken as an example. All the nodes which are to the left will be less than this 21 and all the nodes which are to the right, that will be greater than 21. This is the property of binary search tree which I have already discussed earlier. So for the case 1, if I want to delete 30, then we have to first search where 30 lies. Then we will come at this position. And we have to see whether this 30 has further child or not. But we will see 30 has no children. Then we can say that this lies into the case 1 and we can directly remove this node from here. Then the resultant tree will look like this: 21, 18, 7, 19, 24, 22, 26. This will be the final resultant binary search tree after the deletion of 30, because 30 do not have further child. So we can directly remove this edge, which is pointed by 30. Okay. Next, if I want to delete this node 26, then we have to think about it that 26 has further child or not. Yes, 26 has a child, which is only a single child. Then this will lie into the case 2 category. Okay, which has either left child or right child. Then 26 will be deleted and it will be replaced by its child value. It means 30 will come here and this 26 will be deleted now. Okay, or we can say 30 has been overwritten on 26 and then this node will be deleted. We can say like that as well. Then the resultant node will be 21, 18, 7, 19, 24, 22 and the right child will be 30 because we have deleted 26. We want to delete 26, then whatever its child, either left or the right, it will be replaced here. Let us consider in spite of right child 30, some other child is there which is 25. Then what we have to do in this case? Again, there is only one child which is 25, which is to the left of this 26. Then this value 26 will be replaced by this value, which is 25. And this node will be deleted now. So this is the second case in which if there exists only a one child, then we will directly replace with that child's value. Okay. For the third case, in which I want to delete node 18, then we have to again see whether this 18 has further child or not. We can see here that this 18 has both childs. It has both children. Then what we have to do in this case? In this case, we have to find out in order successor. In order successor of 18. In this case, we have to find out the in-order successor of 18. Then what is this in-order successor? I have already explained this in my previous lectures. First of all, we have to do the in-order traversal of this binary search tree. In-order traversal. What is the concept behind this? That is, first we have to traverse the left child, then we have to traverse the root node, and then we have to traverse the right child. Okay. So in-order traversal of this tree will be left, root, and right. It will be 7, 18, 19, 21, 22, 24, 26, and 30. This is the in-order traversal corresponding to this binary search tree. As if I want to delete this 18, then this value will be replaced by the in-order successor of 18. So what is the successor of 18 here? That is 19. It means this value will comes here. And we will directly delete this H. Okay. So the resultant tree will be 21, 18 because I want to delete this node. This value will be replaced by 19 and then 7 and then 24, 22, 26 and 30. It means we are directly overwriting the value of this in order successor here, and this 18 will come here, and then we can remove this connecting edge. Okay, this is a concept behind the deletion of a particular node inside a binary search tree. Let us understand this concept through algorithm. This is the tree binary search tree deletion case, in which I want to delete a particular node, then first we have to look forward that which case needs to be applied here. If no child exists, then case 1 discussed here. In this we are comparing the root is null. It means tree is empty and we cannot delete any value. If I want to delete a particular node, the first or the second step, in the first step, maybe the tree can be empty. For the second step, if the node exists, then we have to find out the position or the location where that tree item or that item lies. We have already discussed this searching algorithm in my previous or the last lecture, in which we have discussed two operation on binary search tree, which was insertion and deletion. You people can refer this tree search algorithm in my last lecture, from where I was finding out the location of that item, which was I want to find out, as well as its parent position. So by referring that algorithm or the procedure, I may know whether that item is present in the binary search tree or not. If the location is returned as null, it means the data which I want to be deleted is not present and I cannot return that value, and I will simply return this. Okay. In the second case, where if The location of this for the first case, we have already seen in my previous slide that if I want to execute the case one, then if I want to delete a particular node, then it needs to be checked whether that node has both the child or not. In this category for the case one, if I want to delete a node, it means that node should not have any child. Then we can execute this set of operation. We can execute directly by applying all these steps, and we can free that node and return that value. I have already explained all these procedure with the help of example. This is for the case 2. Maybe a node which I want to delete have right child but not the left child. In that case, case 2 will be executed and these steps will be performed. Maybe left child is not null and location of the right child is null. Then these steps needs to be executed here. As per my example, which I have discussed earlier. And this will be the steps for the case tree in which a node which I want to delete exists with both of its children. In then that case, we have to perform we have to find out the in order successor. Through these steps, I am just finding out the in order successor and we are replacing the value of the original node which I want to delete with the successor of that node. And then we can free that original node which I want to delete and I can return. You can execute on your own as well in this algorithm part. Next topic which I want to discuss here is the threaded binary tree. What is a threaded binary tree? As in the linked representation of a binary tree, we have already seen that approximately half of the entries in the pointer fields left and right contains null element. So this space may be efficiently utilized by replacing all these null entries by some special pointers. These special pointers are called threads, and the binary tree which is utilizing all these special pointers or thread is known as threaded binary tree. Okay. What is the utilization of this threaded binary tree? The main utilization of using this binary threaded tree is to make the traversal procedure fast. If I want to efficiently traverse a binary tree, then we can utilize the concept of threading in that. Okay. In a normal linked representation of a binary tree, we have a node which is divided into the three components that was in left child, info, and right child. But if I want to utilize the concept of threading inside this linked representation, then there will be 4 parts. That 4 parts will be, we will have to take a Boolean variable, which will just tell us whether we are using threading here or not. Whether it is right thread or left thread, left child or null, or it can be a left thread, info part, right child, right thread or null. It means this component can have any value either of these three. Similarly, this part can have any value out of these three values. And the first parameter will tell us whether we have used the concept of threading or not. If it will be false, it means we are not utilizing the concept of threading. If it will be true, then we are using the concept of the threading here. Okay. Let us consider an example. This is an example where we have shown the linked representation of a normal binary tree. This will be the info part. This will be the address of the left child. This will be the address of the right child, which is 2000 and 3000 respectively. Similarly here as well, these are the leaf nodes and leaf node addresses. There are no further child. That's why these parameters are null. So we can examine in this linked representation, there are half of the entries, many entries in the leaf nodes are null here. So those utilizing the concept of threading here, we can replace these null pointers with some special pointer, which is a thread. So for distinguishing in between a normal pointer and a thread, there's some representation. If we are using a pointer like this, then it is a normal pointer. It means there is a normal left or right child as per our linked representation. But if we are using a pointer like this dotted representation, then it will tell us the concept of thread. It is a thread pointer. Okay, it is a thread which will make the traversal process efficient. Okay, if I want to draw the threaded binary representation corresponding to this linked representation, it will be where first I will discuss about the threading. And threading can be done in three ways. That can be left threaded binary tree, right threaded binary tree, as well as full threaded binary tree. Let us discuss each one by one. This is left threaded binary tree. In case of left threaded binary tree, this is the left threaded binary as we have seen earlier as well. There is a node which will consist of 4 parts. First part tells whether it is utilizing the concept of threading or not. Then left child, right child or null value. Then info part. Then left child, right child or null value. Okay. Right thread, right child or null. Fine. Okay. First of all, in the previous example, we have to traverse this tree and we have to find out the in-order traversal of this. Okay. The in-order traversal corresponding to this tree, we can do in my next slide as well. The in-order traversal of this tree will be, I'll write down here, 10, 15, 20, 25, 35, 40, and 45. While utilizing the concept of left threading, first we will analyze all the null entries at the leaf node. Then, first we will see, is there any in-order predecessor? For the left threading binary tree, we have to see the in-order predecessor of that particular node. It means we have to see into the in-order traversal. This is the in-order traversal. We have to see, is there any in-order predecessor of this node? No, there is no predecessor. Find out here. That's why this left threading concept cannot be used here. Or I cannot utilize or replace this null value with any special pointer. That's why this Boolean value remains false here. Let's go to the another node. This is 20. Let us find out, is there any in-order predecessor? Yes, 20 predecessor is 15. And we can use the threading concept here. This Boolean value will become true because we are using the left threading concept here. And this null pointer, which was earlier null, this will be replaced by the address of the 20. And address of the 20 predecessor, which is 15. 15 address is 2000. We have earlier seen as well, because 25 left child is, I can write down as well. Let us assume this is 1000. This is 2000. This is 3. This is 4. This is 5. This is 6. And this is 7. And 15 is available at address 2000. That's why we have replaced this null value by 2000, and this special pointer will point to the predecessor, which is 15. Let's talk about the another node, which is 35. Let's find out the in-order predecessor of this, which is 25. 25 is present at location 1000. Then we can replace this null pointer by 1000 and it will point to 25. Another node is 45, and for 45 predecessor is 40, and this value null will be replaced by the 40th address, which is 3000. The value replaced here will be 3000, and this Boolean value will become true because we have utilized the concept of left threading here. Okay, now let's talk about right threading. In case of right threaded binary tree, the right child where we find out the null as a right child, we can replace this value with the in order successor of that particular node. Let us again find out the in order successor, in order traversal of this particular binary tree. That will be 10, 15, 20, 25, 35, 40, and 45. Now we will talk about only the right child. In case of right child, initially there was null, but now this address contains some value. It means we are using the right threading concept here. That's why this Boolean value will become true here. And this value, we will find out the 10 successor, which is 15. And 15, again, we will assign the addresses. And 15 is available at address 2000, and that's why this value null has been replaced by 2000, and right child will point to 15 now. And it is represented by this dotted line because it is showing thread concept, and this is a normal pointer. This solid line is a normal pointer, and this dotted line is a thread. Okay. For the next node 20, the successor is 25, and 25 is present at address 1000. That's why this value here is 1000, and this Boolean value has become true. And similarly, we can proceed for the further nodes as well. We can see here, because here right child is not replaced by null value because there is no in order successor of 45. That's why we are not utilizing the right threaded binary tree concept here, and this Boolean value will become false as it is. If it is utilizing the concept of threading, then it will become true. Otherwise, it will remain false. Now we will talk about full threaded binary tree, in which left node will be replaced by the address pointed by the in order predecessor, and the right node will be replaced by the address pointed by the in order successor of that particular nodes. Accordingly, these Boolean values will get updated. So as per the concept of left threading and right threading, we will combine both of these two concepts in the full threaded binary tree here. So you people can see as well here. Okay. Now we will move forward towards other topic, which is Huffman coding. Huffman coding is basically an application of a binary tree. The main task is to compress the data, okay, to reduce its size without losing any of the details or without the data loss. In order to send any data file over the network, the data file can be compressed and set to reduce the cost of the transmission. So in order to reduce the cost of the transmission, we can compress our original data without losing any of the details. For this purpose, we can use the Huffman coding concept. For doing this task, we have to use the Huffman algorithm. Let's see about this algorithm. First of all, we have to extract the two nodes which will have the minimum frequency out of the given set of elements. It means in the first step, we have to find out two nodes with the minimum frequency. Then we will create a new internal node with the frequency which is equal to the sum of the two nodes frequencies which we have extracted in our first step. Then make the first extracted node as its left child and the other extracted node as its right child. Then we will repeat this procedure until all the nodes has been traversed, and the constructed tree will be known as a Huffman tree. Let us understand this concept with the help of an example. We have to remember all these steps while performing the Huffman coding. Okay. Let us consider this example where few characters are given and some frequency corresponding to these elements are given. Let us divide all these values like this. So we can easily understand what is the specified value corresponding to a character. Okay. First step will be we should assign or arrange all these data items in increasing order or ascending order. It will help us while designing the Huffman tree. Okay. Very first node will be B, then A, after that D, then C, then F, and then E. I am arranging all these data elements in ascending order as per their frequency, which is B is 5, A is 9, D is 12, C is 13, F is 16, and E is 45. After this, as per the algorithm, which we have seen in my last slide, we have to extract two minimum nodes. That's why I have arranged all these data items into ascending order. First, we will extract first two elements, 5 and 9. And the next step, we have to perform the sum of it, which is 14. One child will be 5, another child will be 9. It means as per the algorithm, first we have extracted two minimum weights out of these. Then their sum will be reflected as an internal node, and these will be the first extracted node will appear as a left child, and the second extracted node will appear as a right child. And this will be the sum of these two. After that, the next step will be, again, we will arrange all these data items in ascending order because next term has become 14. Then we can see the next step, that will be 14, which is the internal node. 5 and 9 has been traversed, so we will not encounter all these elements again. Next will be 12, then 13, then 14 internal node will come here, 14, then 16, and then 45. Okay, then again I'll extract two minimum nodes, that will be 12 and 13, and their sum will be first sum will be 25. In the left, first extracted node will be reflected, which is 12, and as a right child, the second extracted node will be represented. In the third, these two has been traversed, so we will not encounter these again. Again, we will arrange the sequence, 14, then 25 will come on later, then 16, then 25, and then 14. You have to notice, I'm also assigning this value of internal node 14 here. I have written here as well. And again, the next internal node value here. Okay. Then again, I will extract two minimum nodes, which is 14 and 16. Now the new structure will be, first extracted node is 14, which will come at the as a left child. Our next extracted node is 16, which will come as a right child. And the sum of these two will be 30. 14 was the internal node, so its subtree will be drawn like this, as it was earlier. Okay, 14 and 16 was the minimum weights. I have calculated the sum of it, and 14 was having a subtree, then it will be drawn like this. In the next step, 14 and 16 has been traversed. Then new item will be 25. Then 30 will come here, and then 45. Then new extracted items will be 25 and 30. 25 will have a subtree. Then it will come as it is. Okay. Next will be 25 and 30. And their sum will be 55. And 25 is having a subtree. So it will be draw earlier, like the earlier way. Okay. Next step. Now these two have been encountered. Next sum will be 45 and 55. First extracted term will be 45, which will come at the left hand side. Okay. And 55. And the sum of this will be 100. 45 will come at or will be reflected at the left hand side because this is the minimum first extracted node and the second one is 55. It will be drawn like this. 25, 30 will come here, then 12, and then 13. So this constructed tree will be our Huffman tree. 30 was also there, so 30 subtree will also be drawn here. 30, yes, in my this step as well. 30 was a internal node and its subtree will be 14, 5 and 9. It was not a new node, it was an internal node. That's why I have to include this as well. Okay, 30, then 14, 16 and 5 and 9. You can accordingly draw it because I have shown it here. You can draw the final structure of this. Okay, if you want, I can draw the final tree here. 100, then 45, and then 55. In 55, there was a subtree, 55, and then 25. 25 has further child, which was 12 and 13, and 30. This was the internal node, okay? 30, which has further child, that was 14 and 16. 14 and 16, and it will have 5 and 9. So this will be our final Huffman tree. Okay. If I want to find out the unique code corresponding to each, then we can assign the values corresponding to this Huffman tree. All the nodes which are lying to the left, that will be assigned as 0. All the nodes which are lying to the right side, that will be assigned as 1. Similarly, for 55, all the nodes which are to the left will be 0, 0, which are to the right will be 1. It is right, then it will be 0. This will be left, 0. This will be left, 0. This will be 1, 1. Right, 1. This will be right, 1. Then we can find out the unique code corresponding to each one of them. Then for B, which was assigned the weight as 5, the path to be followed to reach till 5, to reach this 5 will be this, 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 and this. So the sequence corresponding to this B will be 1, 1, 0, 0. It will be 1, 1, 0, 0. And this will be a unique code. No other character will have the same code. Okay. This is a unique code. So by defining the Huffman tree, we can also encode all these characters. Okay. This is 1, 1, 0, 0. Then we can reach to 5. For 9, which is character A frequency, the path to be followed will be 1, 1, 0, 1. 1, 1, 0, 1. For D, which is 12, the path followed will be 1, 0, 0. For 13, which is C, that will be 1, 0, 1. For 16, which is F, that will be 1, 1, 1. For E, which is 45, the frequency code will be 0. Because it is to the right of this, it will be 0. So this is, you can see here, no code or no two characters will have the same code. That's why we can also provide the unique code corresponding to all these characters. Okay, this was all about Huffman tree. This is the reference which I referred. In the next slide, in my next video or my lecture, I'll discuss about AVL tree insertion, and AVL tree deletion. Thank you, and thank you for the patience listening.